started the discussion on the problem of recognition of temporal patterns. That is, we said that we can have patterns which actually unfolds in time. So, the examples under this category is one you can consider is a speech recognition problem, because we know that the speech signals are actually time varying signals. So, at different instants of time we have different signal properties, or we have different signal strength. So, speech is one of the signal which is actually a time varying signal, and for speech recognition purpose what people usually does is the speech signal is divided into a number of phonemes, and you try to find out in which sequence the phonemes occur, and based on that you try to recognize or you try to classify the word that has been spoken. So, the other applications in this temporal pattern recognition may be, say, activity recognition. Say for example, we want to find out whether some person is walking, some person is running, somebody is crawling and all that. It can be, say, sign language recognition, because sign language is basically you expressed your ideas by using hand movements, and it is the sequence in which the different parts of the hand move that actually gives you or sends you the information, or you have to decode that particular sequence of hand gestures, and from the sequence you have to interpret what message is being conveyed. Similarly, the activity recognition, when I say running, walking, crawling, this kind of applications is very useful for security surveillance purpose. So, we want to identify whether the movement of a person is a normal movement or it is an abnormal movement. So, through a video camera, if I can capture that the movement of a person is abnormal, which obviously has to be detected based on the kind of movement that the person does, and obviously it is a temporal sequence. So, when I say the movement, it is the body pose at different instants of time which occurs in a given sequence, in a particular sequence, and based on that the body pose at different instants of time, you try to identify whether the movement is a normal movement or abnormal movement. And if the movement is abnormal, you try to track that person, because definitely a person going through an abnormal movement is a suspicious person. So, this temporal sequence or the patterns having temporality in it have lots of applications. I have just given 2 or 3 examples, but there are many other applications, application domains in which these temporal sequences need to be analyzed and they need to be classified. Now, what we said in our previous class is that to recognize or to identify such temporal sequences, what we do is we make use of a machine which is something similar to, very similar to our sequential machine or finite state machine. So, as in finite state machine, we have a finite set of states through which the machine makes transition. We have a finite set of output symbols, we have a finite set of input symbols. So, if the machine is any state, say S I at time instant t, the machine will go to another state at the next time instant depending upon the input that is fed, and when it makes a transition to the next state, it emits an output. So, accordingly, for a sequential machine, I can have state transition table, that is based on which input to which of the states the machine makes a transition. And similarly, I can also have an output table, that for which type of transition, for transition from which state to which state, what is the output that the machine generates. And it is this output which is actually observable. The state of the machine is not really observable. So, I can identify the state from the input that is given and the output that is generated. So, as in case of a sequential machine, we have said in the previous class, in a sequential machine, if the set of outputs is limited to only two symbols, that is 0 and 1, the sequential machine or finite state machine actually becomes a finite state automata. And such a finite state automata has got huge application in sequence generation, bit sequence generation or bit sequence detection. So, bit sequence detection is a problem which is very, very useful in communication, because this is what gives you the synchronization. If I want to identify a point from where information starts, okay, so the starting of that information can have a particular bit sequence, and I can have a finite state automata to detect that bit sequence. And once the bit sequence is detected, then I can say that the next portion of the sequence actually gives me the information, but the sequence which is detected is only for the synchronization purpose. So, similarly, in case of hidden Markov model, we have said that there are two types of states. One kind of state is, say, omega. So, this set of states, we said they are the hidden states. These states cannot be observed by the perceiver. And we have another type of states which are actually visible states, and that type of states is called, say, V. So, this is a state of visible states. So, a hidden Markov model can have a number of hidden states, and it can have a number of visible states. So, let us take an example having a hidden Markov model having, say, 3 states. So, I have under omega, I have states omega 1, omega 2 and omega 3. So, these are the 3 states of this hidden Markov model, say theta. We are saying a model as theta, and V is the set of visible states or the symbols, visible symbols, which are emitted by this hidden Markov model when this HMM theta is in a particular state. Okay. So, let us assume that this can generate, say, 3 visible symbols V1, V2 and V3. So, let us draw this HMM theta. So, we have the states omega 1, omega 2 and omega 3. So, the machine of this hidden Markov model can make a transition from state omega 1 to state omega 2, where this probability of transition is given by A12. As we said that if the hidden Markov model is in state, say, omega I at time instant, say, t minus 1, and it makes a transition to state omega j at time instant t, and the probability of such transition from state omega I to state omega g is denoted by Aij. So, from omega 1, this hidden Markov model can make a transition to state omega 2, where the probability of transition is given by A12. Similarly, from omega 2, it can have a transition to omega 1, where the probability of transition is A21. Similarly, A13, A123, it will be A13, omega 3 to omega 1, this will be A31, omega 3 to omega 2, it will be A32, omega 2 to omega 3, it will be A23. So, these are the transition probabilities between two different states. Now, in every state, the machine can emit one of the visible states. In each of these hidden state, the machine can emit one of the visible states. So, from omega 1 it can generate, it can emit the visible symbol or visible state omega v 1 with a probability of this emission which is given by v 1 1, because as we said that the probability that the machine emits v k when the machine is in state omega j, this is actually given by b j k. So, from state omega j it emits a symbol, a visible symbol v k with a probability which is given by b j k. So, from omega 1 it emits a symbol v 2 with a probability b 1 2, it emits v 3 with probability b 1 3. Similarly, here it will be v 1 is emitted with probability a 2 1, v 2 is emitted with probability b 2 2, v 3 is emitted with probability b 2 3. From omega 3, v 1 is emitted with probability b 3 1, v 2 is emitted with probability b 3 2, and v 3 is emitted with probability b 3 3. So, these are the different probabilities of emission of the visible states from different hidden states of this hidden Markov model. Now, we find that given any state, there will always be a transition to some of the states, including the state itself. So, I can have a transition from omega 1 to omega 1 also, and this transition probability will be a 1 1. Similarly, omega 2 to omega 2, this transition probability will be a 2 2. Similarly, omega 3 to omega 3, this transition probability will be a 3 3. So, this is also possible, that is in two different time steps, two subsequent time steps, the machine can be in the same state, same hidden state. So, because from any hidden state there is always a transition to one of the states. So, naturally sum of a I j for when I take the summation over all j, this will be equal to 1, and that will be true for all values of I, because from any state the machine always makes a transition to one of the states. So, the sum of the probabilities a I j when I take the summation over j, that has to be equal to 1, and that has to be true for all I. And similarly, when the machine is in any state, it always emits a visible symbol. So, because it always emits a visible symbol, so I must have b j k when I take the summation over k, because v k is the symbol and b j k indicates that from hidden state omega j, the machine emits a visible symbol v k, and it always emits a symbol. So, this b j k sum over all k, that also has to be equal to 1, and this will be true for all j, that is for all the hidden nodes. So, given this, and we have also said that a hidden Markov model has a specific hidden state which is called a receiving state or an accepting state or a final state. And we have said that once the machine reaches that state, it cannot come out of the state. So, all the transitions will be within that accepting states only, and while in that accepting state, it will emit only one visible symbol, say V 0. It will not emit any other visible symbol. So, by incorporating that accepting state into our hidden Markov model, I can redraw this hidden Markov model something like this. So, I have this omega 1, I have say omega 2, I have omega 3, and this is the accepting state which is omega 0. So, from omega 1 to omega 2 I have transition A1 2, omega 2 to omega 1 it is A21. Similarly, all these different transitions So, up to this it is fine. I can have self transitions. This is A11, A22, A33. But from any of the state, it can make a transition to omega 0. So, I can have this sort of transition. So, here it will be A10, A20, A30. But once the hidden Markov model is in this final state omega 0, it cannot come back to any of these states. However, it can have transition within the state, and because this transition will always be within omega 0, so I must have A 0 0 is equal to 1. And within omega 0, it emits only one visible symbol, which is V 0. So, you find that the probability of emission from omega 0, that is B 0 of the symbol V 0, that will also be equal to 1, because this is the only symbol which is emitted from this accepting state. Whereas, for all other states, they have V 1, V 2, V 3. Similarly, from here I will have V 1, V 2, V 3. From here also I will have V 1, V 2, V 3 with the respective probabilities of emission. So, here from omega 3, V 1 will be emitted with a probability B 3 1. Similarly, V 2 will be emitted with probability B 3 2, and so on. So, this is the final hidden Markov model that we are going to use for our temporal pattern recognition. Now, given such a hidden Markov model, you find that in hidden Markov models, there are three central issues which need to be addressed. So, what are the central issues? In hidden Markov model or HMM. The first issue or the first problem is an evaluation problem. The second problem is what is called a decoding problem. And the third problem is, which is very important, not only in case of hidden Markov model, a very important problem in all the classifiers is the training of the classifier or the classifier learning, because unless the training is done properly, the classifier cannot classify the patterns. So, the third problem, which is a very important problem, is the learning problem. That is, how the hidden Markov model is actually learns the patterns, or how do you train the hidden Markov model. Now, what is this evaluation problem? Let us come to this problem first. We said that when we have a hidden Markov model theta, when this hidden Markov model theta is specified, we say that we have three things. Okay. One is the number of hidden states, the number of, or what are the hidden states? We have the visible states or visible symbols. we have the transition probabilities Aij whenever the hidden Markov model makes a transition from state omega I to state omega j. We have the transition probabilities corresponding to the visible states, okay, though it is actually an emission probability, but all the visible symbols are also considered to be visible states. So, we can also call that as a transition probability. So, it does not matter whether we call it a transition probability or we call it an emission probability. So, we have to have the transition probability Aij for all A and all j, and we have to have the transition probability Bjk or the emission probability Bjk, which is the probability of emission of the visible symbol Vk or visible state Vk from the hidden state omega j. So, the model theta is specified by omega, that is the set of hidden states, V the set of visible states, Aij for all values of I and j which are the transition probabilities, state transition probabilities, and Bjk which is the which are the visible symbol emission probability. So, once you have such a hidden Markov model theta and you have a sequence of visible symbols Vt, which is a sequence of length capital T. So, this evaluation problem is that given this Vt and theta, we have to find out what is the probability that Vt was generated by theta, okay, which is expressed as. So, this is what is the probability that this visible sequence Vt was generated by the hidden Markov model theta, where theta is specified over here. So, this is what we want to find out, and this is represented as probability of Vt given theta, okay. And this is the problem which is evaluation problem. And obviously, once we can evaluate this probability, we can try to classify this visible sequence Vt, provided we know what is this hidden Markov model. So, you find that in case of hidden Markov model for recognition of temporal sequences, if I have say C number of sequences and an input sequence or unknown sequence is to be classified to one of this C number of sequences. Okay. So, I have C number of model sequences. For every sequence, I have to have a hidden Markov model theta. So, theta 1, the first hidden Markov model, will encode or will represent the first sequence, first model sequence. Theta 2 will be for the second model sequence, theta 3 will be for the third model sequence, and so on. So, once we have so many models, say theta 1 to theta c, theta 1, theta 2 up to theta c, if I have c number of classes, or if the input sequence is to be classified into one of the c classes, for every class I have to have a hidden Markov model. So, every theta 1 will have corresponding omega, that is the set of hidden states. It will have corresponding V, that is the set of visible states. It will have corresponding Aij, it will have corresponding Bjk. Theta 2 will also have its corresponding omega, V, Aij and Bjk and all that. So, every sequence or every class is represented by a separate hidden Markov model. So, given an unknown sequence Vt, we have to find out what is the probability that Vt was generated by theta 1. We have to find out the probability, what is the probability that Vt was generated by theta 2. Similarly, what is the probability that Vt was generated by theta c. And from all these different probabilities, then we can apply the Bayes rule to classify the input visible sequence Vt. Okay. So, the evaluation problem actually deals with this, that given a model theta and given a sequence Vt of visible symbols, we want to find out that what is the probability that Vt was generated by this model theta. Okay. So, this is what is my evaluation problem. Now, the decoding problem says that I have this Vt and I have generated these probabilities. Okay. What is the probability that Vt was generated by the model theta? The decoding problem says that what is the most likely sequence omega t of the hidden states which had led to the generation of Vt. So, we want to find out that sequence omega t that has led to the generation of, or which has generated this sequence Vt. Okay. So, that is what is the decoding problem, and the learning problem is given a coarse structure, a rough structure of the hidden Markov model. So, when I say a rough structure means that how many hidden states this hidden Markov model has and how many visible states this hidden Markov model has. So, that is what is a rough structure of a hidden Markov model, but I do not know the probabilities of transitions, the transition probabilities are unknown. So, through a set of given training sequences, I have to find out these transition probabilities. So, I know what is omega, that is the set of hidden states. I also know what is V, that is the set of visible states. So, these two are actually known. What I have to find out is, I have to use a set of training sequences, a large number of training sequences, and using those training sequences, I have to estimate the transition probabilities Aij and Bjk. So, these two transition probabilities are to be estimated. So, this is a problem which is known as learning problem, and as we said that this learning problem is one of the is a very important problem, not only in case of hidden Markov model, but for designing any classifier. Okay. So, we will take up these central issues, the evaluation problem, the decoding problem and the learning problem one by one. So, first let us take up the evaluation problem. So, as we said that evaluation is nothing but given a hidden Markov model theta and a sequence of visible states Vt, I have to estimate what is P Vt given theta. That is, what is the probability that this model theta has generated this sequence of visible states Vt. Okay. Now, find that what I can do is, I can try to find out all possible sequences of the hidden states of length t or length capital T. So, that means I want to find out, or I can, that is the crude approach, that all possible sequences of omega t. So, as we said earlier that this omega t is nothing but sequence of t number of invisible states. Okay. So, when I have in theta a number of invisible states, I can find out all possible sequence of t number of invisible states. And for each of this sequence, I can try to find out what is the probability that that particular sequence of hidden states omega t has generated this visible sequence Vt. Okay. So, what I can say is in a crude form, this p v t given theta, this can be estimated as, I can find out what is p v t given say omega r t. Now, why I am writing omega r t is, I said that I want to find out all possible sequences of hidden states of length capital T. This index R indicates one of those sequences. Okay, it is one of those possible sequences. So, I can find out what is p v t given omega r t, that is one of the possible sequence, which is to be multiplied by probability of omega r t. That is, what is the probability that this Rth sequence occurs. And if I take the summation of this for r is equal to 1 to r max, where r max is the number of such possible sequences that I can generate. Okay. So, if I take the summation for r equal to r max of this, then what I get is p v t given theta, that is the probability that this sequence of visible states v t is generated by this model theta. Okay. Now, over here this omega r t, as I said that this is nothing but omega at time instant 1, omega at time instant 2, continues omega at time instant capital T. So, this is the sequence, where for different sequences I will have different values of omega 1, omega 2, omega 3 and so on. Okay. Now, find that if there are say capital T number of hidden states, if there are T number of let me put it, because T we are using for something else. So, let me say that if there are capital N number of hidden states, this is the number of hidden states. Then you find that R max will be of the order of n to the power t. So, this is R max is n to the power t. So, I will have n to the power t number of possible sequences of hidden states of length capital T. So, this is what is the value of R max. And here I can compute, you can compute that this P r of P omega r t, because this is nothing but the sequence of states, sequence of hidden states of length capital T. So, I can easily estimate that P of omega r t, this is nothing but P of omega t given omega t minus 1. From a state at time instant t, it from a state at time step t minus 1, it makes a transition to state omega t. Okay. And because this is a sequence of t number of such states, this is actually the probability of transition from a state at time step t minus 1 to another state at time step t. So, this is nothing but a probability of transition. And from a particular sequence, if I multiply this probability of transitions, so what I have to do is I have to multiply this over t is equal to 1 to capital T. Okay. So, if I take a product of this transition probabilities from t equal to 1 to capital T, that gives me what is the probability of a particular sequence of hidden states. So, this P R T is nothing but this, and these are nothing but transition probabilities. So, this P R capital T, P omega R capital T is nothing but the product of the transition probabilities from one state to another at subsequent, at consecutive time steps for this rth sequence of invisible states or hidden states. Similarly, I can also compute P of V t given omega r t. Okay. So, you find that this is a visible symbol. If I take a particular instant, say first instant, the visible symbol, the first visible symbol is emitted by the first state in the sequence omega r. So, this is nothing but the probability of emission of visible symbols. So, accordingly, I can write this in the form, this is the probability of emission of visible symbol at time step t given the machine is in state omega at time step t. And the product of this from t equal to 1 to capital T, that gives me what is the probability V t given omega r t. And you find that this is nothing but the product of BJKs, the corresponding BJKs, and every BJK will come from the hidden states in omega r t. So, because of these two, I can now write this P V t given theta. You find that P V t given theta was this expression of P V t given theta. Now, in this expression, if I put P of omega r t and P of V t given omega r t, the expressions of these two, which we have said, we have just seen are the product terms. So, I can write P of V t given theta will be is equal to product P V t given omega t into P omega t given omega t minus 1. So, you just look at this expression and this expression. So, this is nothing but this and this is nothing but this. Okay. So, I have to do this take this product for t is equal to 1 to capital T and take the summation of this over r is equal to 1 to r max. So, given a hidden Markov model theta and a sequence of visible states V t, I can find out the probability that this model theta has generated this hidden this sequence of visible symbols V t as by this expression. Now, find that if I look at the complexity of this particular expression, the complexity of this expression will be of the order of n to the power t times t, which is huge. So, I have to have a high number of computations, a very large number of computations to find out this P V t given theta. So, instead of using this direct expression for computation of P V t given theta, I can make use of a simpler approach. I can make use of a recursive algorithm, the algorithm which will use that given a sequence of visible symbols V t, what will be the probability that the hidden Markov model will be in a particular state at a particular step in time. So, how is that possible? Let us just try to explain it conceptually. So, I have a number of states, and as I said that one of the states that I have is an accepting state or an absorbing state or a final state omega 0. So, I have state omega 0, omega 1, omega 2, like this I have omega I, continues. I have a number of states. Okay. So, I will put it like this. So, these represent states, and at different time steps I will have same number of states. So, this is the time step 0, t is equal to 0, this is at t equal to 1. Similarly, I will have this is the t minus 1, I will have time step t. It continues like this. Okay. So, the first row indicates omega 0, second row is omega 1, omega 2, say omega I, somewhere I will have omega j and all this. So, you find that if somehow I know that at t equal to 0, what is the hidden state in which the machine is. So, let me assume that at t equal to 0, the machine is in hidden state, say omega 1. Okay. Then I can find out that at t equal to 1, what is the probability that machine will be in state omega 0? What will be the probability that the machine will be in state omega 1? What is the probability that the machine will be in state omega 2? What is the probability that the machine will be in state omega I, and so on. The reason is, from omega 1 it can make a transition, it is possible to make a transition to omega 0, it is possible to make a transition to omega 1, omega 2, omega I, like this. So, if Vt, in Vt the symbol V1, so if V1, the symbol V1 is equal to V0, which is the visible state emitted by the final state only. Okay. So, if this is equal to this, then obviously from omega 1 I will have a transition to omega 0, because it is only this omega 0 which can emit this V0, and in time step 1 I have this visible symbol V0. So, if this is the case, then from omega 1 I definitely have a transition to omega 0. If this is not the case, if V1 is not equal to V0, then obviously from omega 1 the model has not made a transition to omega 0 at time step t1, t equal to 1. It has made transitions to some other steps. Now, let us consider that any of the state. So, I have said this time state step t and so on. Okay. So, let us consider this particular state omega 2. Okay. So, what are the possible ways in which the machine can come to this state omega 2? Obviously, from omega 0 it cannot make a transition to omega 2, because as we said that if the model enters this final state omega 0, it cannot come out of that state. So, from omega 0 it cannot make a transition to this state omega 2. However, it can make a transition to omega 2 from omega 1, it can make a transition from omega 2 to omega 2, it can make a transition from omega 3 to omega 2, it can make a transition from omega I to omega 2, and so on. Now, if somehow I know that what is the probability, I have been able to compute the probability that the machine is in state this omega 1 at time instant t minus 1, and that is given by alpha 1 t minus 1. Here it is alpha 2 t minus 2. Here it is alpha I t minus 1. So, this is the probability that the machine is in these states at time instant t minus 1. Then I also know that what is the probability that the machine will make a transition from omega 1 to omega 2, which is given by the transition probability A 1 2. So, the probability that the machine can make a transition from omega 1 to omega 2 in time step t is given by this alpha 1 t minus 1 into a 1 2. Plus, I also have a possibility that the machine will make a transition from omega 2 to omega 2 itself, and this transition probability is a 2 2. So, the probability that the machine makes the transition from omega 2 to omega 2 is nothing but alpha 2 t minus 2 into t minus 1 into omega 2 into a 2 2. Here it is alpha 1 t minus 1 into a 1 2. Here it is alpha I t minus 1 into a I 2. Okay. And here if I make the sum of all these products, what I get is the probability that there will be a transition from one of the states, from any of the states in time step t minus 1 to state omega 2 in time step 2. And I also know what is V t. That is the visible symbol in time step t. And this visible symbol in time step t can be emitted by this state omega 2 with a probability b 2, and suppose this emitted symbol is a v k. So, this will have a probability b 2 k. So, finally, I can say that the probability that the machine is in state omega 2 in time step t after emitting first t number of visible symbols from my sequence of visible states v t is given by sum of all these product terms multiplied by this b 2 k. So, by using this logic, I can simplify or I can have a recursive algorithm to find out the probability that the sequence V t was generated by hidden Markov model theta. So, for that what I do is I define the term say alpha j t, which as we have just explained that this alpha j t, okay, this simply says what is the probability that the machine will be in state omega j in time step t after emitting first t number of visible symbols in the sequence of visible symbols V of capital T. Okay. So, that is what is this alpha j t, and we can define that this alpha j t will be equal to 0 if t equal to 0 and j is not an initial state. T equal to 0 means we are talking about our initial condition as per this diagram. Okay. And the probability, as I said, that if I know that the machine is initially in state omega 1, right. So, I am saying that this is equal to 1, the probability of omega 1 in time step t equal to 0 is 1, the probability that the machine will be in any other state, any other states will be equal to 0. So, this is as per definition. I said omega j t is equal to 0 if I am in the initial state, that is t equal to 0, and this j is not an initial state. If it is an initial state, then this will be equal to 1, that is t equal to 0 and j is initial state. Otherwise, I define this alpha j t as sum of alpha I t minus 1 into a I j into b j k v t. You come to this diagram that we have drawn. Okay. this is if I take the product of all these, if I take the sum of all these products, this is equivalent to sum of alpha I t minus 1 into b I j. That is the transition probability from the ith state to the jth state times b j k v t. So, here what we have said is, if v t is equal to v k, then I take the emission probability or transition probability b to k, that is from the jth state at time t, whatever symbol is emitted, I choose only that corresponding probability to decide what is the probability that the machine can be in state omega j at time step t. Okay. Because I know what is the tth visible symbol in my sequence of visible symbols. So, I can make use of that. So, this is what I have. So, this b j k v t indicates that this b j k, the probability of transition, is chosen by the tth visible symbol. So, if v t is equal to v 1, this will be simply b j 1. If v t is equal to v 4, this will be b j 4. Okay. So, I make use of this particular definition. And using this definition, now I can write an algorithm to find out what is the probability that the machine theta or HMM theta has generated this sequence of visible symbols V capital T. Okay. So, I write an algorithm and in particular I call it as forward algorithm. The reason is why I am writing forward is I will make use of a similar algorithm, but that is called a backward algorithm, and both this forward algorithm and backward algorithm will be used in our third issue, which we have said learning of the hidden Markov model. So, there we will use forward and backward algorithm, both of them together. So, I will simply write this forward algorithm. So, obviously, the first one is initialization state. So, I have to make time step t equal to 0. I have to know what is aij, I have to know what is bjk, I have to know what is vt, because actually this is the one for which I am trying to find out the probability, and I have to initialize alpha j 0. Okay. So, this depends upon if initially I assume that the machine is in state omega 1, alpha 1 0 will be equal to 1, alpha 2 0 will be equal to 0, alpha 3 0 will be equal to 0, and so on. And then I go for recursion. So, what I do is for t increment t, alpha j t will be b j k v t, the same one, into sum of alpha I t minus 1 into a I j, where I varies from 1 to n, as I have n number of hidden states, and this has to continue until t becomes equal to capital T, because I have to take all the symbols from the given sequence of symbols. So, this has to continue for till t becomes equal to capital T. And at the end of this, what I have to do is I have to return p v t given theta, which is nothing but alpha 0 t, and this alpha 0 is the probability of final state. So, this is for final state, and the algorithm stops there. So, this is the algorithm which can be used, called forward algorithm, which is used to find out what is the probability that a given sequence V t is generated by given model theta. Okay. And while doing so, we have also found out that in every step, what is the probability that the machine can be given in a particular hidden state. Okay. So, I will stop this lecture now. In the next lecture, I will explain this algorithm further with an example. Thank you.